Okay, so this topic, this last example is going to be talking about, we'll call this example 4, exponential growth and decay models. And so there's really, it's the same formula, but one has a plus and one has a minus in it. So the plus is going to be if it's growth. We're always going to start with our baseline of 1, and I'll explain with a graph why that's 1 plus r and 1 minus r. But the way the growth works, if it's a problem like growth, you're going to see words like increases or accumulates or gets higher. Decay would be decreases, gets smaller as it goes, that kind of stuff. So growth increases, decay decreases. This little a is just going to be your starting value. You're probably used to seeing that a times b to the x. This is your b. Now we can break your base up into 2 components. One plus some r value. That r is a rate, and usually our rate is given to us as a percentage. So we need to convert that to a decimal, and we'll review how to do that. And your exponent is your variable. In this case, it's usually represented by time. So some sort of time increment, like months or years or days or hours or whatever that time increment is. So to understand what the 1 is doing, if you look at a problem like 5 times 1 to the x power, you're going to notice that it's just a flat line, because if I raise 1 to any power, it's not going to change that. 1 to the 5th power is still going to be 1. 1 to the 100th power is 1. So that's 5 times 1. That's going to give you 5. That's why it's a flat line. But if I make that number bigger than 1, let's say I make it 0.01, then the graph changes a little bit. All right, if I zoom out, notice that it does become an exponential function. That rate of increase is this component, 0.01, which is 1%. So 2% would be 0.02, 3%, 0.03. And notice when that rate of increase increases, then the graph becomes steeper. So there's a 5%, maybe a 10% increase would be even steeper. A 90% increase, super steep. And you've seen 2 before. That base of 2 means that's a 100% increase, because 1 plus 100%, which is 1, is 2. So 2 represents a 100% increase. We can also show decay by saying, well, instead of 1, maybe 0.99. And so that's going to be a 1% decrease. That's a decay. So notice it's going down as it goes to the right. So a 2% decrease would be even steeper. You could make a 10% decrease, 90%. A 20% decrease would be 0.8. All the way down to, you know, a 99% decrease. At that point, it's almost a flat line there. So you can have really sharp decreases or increases depending on your rate. So let's talk about some of the setups for these. So let's look at question number 1. We'll do this one together. You buy a savings bond for $25 that pays a yearly interest rate of 4.2%. We first want to write a function to model the situation. So jot this down, and what we're going to write is your a is just going to be your y value. Okay, so that's you can call that a. I usually just call it capital A. That's your ending amount. Your initial amount is always going to be given to you in these type of problems, and there'll be some problems we'll have to solve for it, but this is your initial amount. That's your first number you write after the equal sign. In the base, because that is going to be a savings bond for $25 that pays a yearly interest rate of 4.2%, pay would imply that it's going to be growth. So we want to add the rate. So that 4.2%, as a decimal, you can move that decimal over 2 spots to the left, and that's going to be 0.042, or you can take 4.2%, means out of 100, so 4.2 divided by 100, and you can put that in your calculator, and that'll give you 0.042. So we're going to do 25 parentheses 1 plus 0.042 raised to the t power. Now we want to simplify that. So 25 parentheses 1 plus 0.042 is 1.042. You can add those together. And that represents your function. So the next component of that will be having to plug in a number to evaluate it. So in this case, it says, what will the savings bond be worth after 15 years? So we want to know our final amount. Given that I start with 25, I have an increase, so I'm adding to 1 of 4.2%, and I'm going to raise that to the 15th power. That's your t value. We'll plug that in the calculator. And we're going to get a smaller number, a bigger number than 25, but it's going to have some decimals to it. So we'll just round that. Since we're talking about money, usually money is in dollars, $46, and this is 33 cents, but then that 9 is going to bump that up to 34 cents. So I would say $46.34 when I answer that question. 46.34. We'll put a little dollar sign in front of it since it does represent money. 10. Okay, let's look at question 2. See if you can read through this and identify the rate, the initial value, and maybe even come up with a function. Decide if it's going to be exponential growth or decay. So pause the video and try this on your own, or at least get it started. And then I'll kind of help you finish it up if you need help. Okay, have you identified the initial population? That's going to be 50,000. That's your little a value. Is this a growth or decay? What word would imply that it might be growth or decay? I would say losing means decay. So you're going to subtract that rate from 1, not add it, because we want that number in the base to be between 0 and 1 if it's decay. So your rate is 2.6% out of 100. Moves the decimal over 2 spots, and that's going to be 0.026. And so that function would be a equals 50,000, parentheses 1 minus 0.026 to the t power. And 1 minus 0.026 is 0.974. So a equals 50,000, parentheses 0.974 to the t power. That's your function. So notice that that number is between 0 and 1. It's going to be losing people. Now we want to know how many people are going to be there after 8 years. So we can then take your 50,000 times 0.974 and plug in 8 for your exponent. And let's see what that gives us. So after 8 years, with losing 2.6%, looks like we're going to have a population of about 40,498.75 people. 40,498.75. And this is people, so there's no sense to have decimals. So I would just, since that's more than half a person there, I would just round that up to 4,499 people and just give a whole number for that. All right, let's look at this last problem here. We have an exponential decay model. No context, but we're given y equals 3 times 0.962 to the x power. We want to know what is the rate of decay. So we know this is going to be decay because this number right here is between 0 and 1. So we need to focus on this number here. We know our initial value is going to be 3. And we know this is decay, so that's going to be 1 minus r. So if I look at 0.962, and I know 1 minus your rate will get you that decay, then I could solve that for r. If I move the r to the left side of this equation and make it r plus 0.962 equals 1, then I can just subtract 0.962 from 1. So let's do that. And your rate is going to be whatever that equals. So I like to think of this as 96.2%. How many percent will get us up to 100? And I think that's going to be 3.8%. But we can always check it in the calculator. 1 minus 0.962 is 0.038. Now we want to know this rate of decay, and when we're representing a rate, we want to write that as a percentage. So if your rate is 0.038, the percent that would be, since you're going from a decimal to percent, you're going to go move that decimal 2 places to the right, or times by 100, and that's going to give you 3.8%. So that's a 3.8% rate of decay in this particular problem. And if it was like a growth problem and it said like 1.052, and that was like 3 times 1.052 to the x power, then that growth would be this portion, which is 5.2%, just because it's added a 1. Anyway, hopefully that's helpful for your assignment. And let me know if you have any questions. Thank you for watching.